two seminars. First one from Lisa from the University of Michigan. I don't think she needs much introduction, well known by everyone. So she's going to talk about prediction on networks with Cohesion.
Right, thank you. This is on, right? So thank you for the invitation. This was, in case you didn't see this was designated as informal seminars, which hopefully is a good excuse for me to say that I just finished writing this 10 minutes ago, and I haven't given this talk before, so it probably will look a little bit informal. But I'll try to at least communicate the main idea, and the main idea is a new direction for me, and I think it's somewhat different from what people have been mainly talking about so far in the program. Maybe not so much from what they will be talking about this week in applications, but let's just excuse the informal aspects of it if they show up suddenly. So this is joint work with my PhD student, Chang-Shi Li, and also my colleague at Michigan. Microphone here. I don't see a light here. I see. No. Now it's working. Is it? No, I don't think that's the thing. Okay, is that better? I think it's on now. That's the main difference. Thank you. Okay, so the motivation for this work. I'm going to skip the whole introduction to networks part because everybody here knows about networks, and there has been a lot of work that's focused on analyzing one single network, usually in the form of a binary adjacency matrix, and we have many tools to do this, and people have focused on things like community detection and link prediction and some other problems, and I've contributed to that line of work as well. But as we know, and some people have repeatedly pointed this out early in the program, often, and maybe even most of the time, there is in fact a lot of other information that's contained in the data. There are things that covariates, that look like covariates on the nodes and the edges, sometimes timestamps, etc. And one way in which one can use them, and that has also come up before, is to help with the same network tasks that you would be doing on a single adjacency matrix, say community detection. You can do covariate-assisted community detection, for example, and so on. That's not what I want to do here. What I would like to do is turn it around and be more of a statistician here and say there are many other questions we can ask here. Typically, actually, when we have a lot of covariates, we're often trying to do something with the covariates, say prediction, and can we use the network to help us in our other statistical tasks? So it's the other direction. I'm not going to use covariates to help me, say, do community detection. I'm going to do prediction, specifically in this talk, and see if the network can help me do prediction better. So how can a network help you do prediction better? Well, the particular property that we'll try to exploit here is cohesion. And I'll say right away that cohesion is not a strictly defined term, and I think different people use it to mean different things. I'm just going to use it generically. I think in Eric Kalashik's book, there's a whole chapter explaining different kinds of cohesion and what people might call that word. But what I mean by that is just that nodes that are linked, nodes that, say, in a social network are friends, tend to have more similar characteristics than nodes that are not. So if you have, say, a high school friendship network, a student whose friends smoke is more likely to smoke as well, right? So empirically, people know this happens in social behavior studies. I'm mainly focusing on social networks here, people. So empirically, it is observed. Why it happens is a much more complicated question, and it can happen for at least two reasons, maybe more than two, but at least two commonly recognized reasons. One is what people call homophily, And in this example, that would mean these two students became friends because they're both smokers. So they have similar characteristics, and that's why they become friends. Or the other thing that could happen is what's called contagion on the network. And that means a student made friends with those who smoke, and then the student started smoking because all their friends smoke. So you can immediately see when you formulate it like this, there is a causal question, there is a causality direction. And this social data is typically observational, and establishing causality is very hard. And in fact, there's a very nice paper that Cosmo Shalizi wrote with a co-author showing that it is, in fact, not possible to distinguish homophily from contagion in this context if you have observational data. You just cannot tell from the network if you observe a static network which one it is. So I don't aspire to do that, let alone it's not even possible, but I'm not trying to do a causal analysis here. All I'm trying to do is a simpler thing, is improve prediction. Yeah.
So I guess there is a third possibility that both of them are causal effects of some third variable.
Oh yeah, absolutely. No, I said at least
people on this side of the river tend to smoke and be friends with each other.
Absolutely. So that's why I said at least two things that people sort of describe in those words. But of course, it could be both, or some other thing, or all of the above. Yeah, which makes it even harder. Right. But I'm not going to worry about how this phenomenon arose there. I'm just going to try and exploit it. So just to show you an example, if you've ever listened to talks on community detection, you've probably seen one of these school networks, maybe not this exact one, but there are many. This is the adolescent health study, is an enormous longitudinal study in the US, carried over a number of years, and this data, a lot of people use the public version of the data, which is very much reduced. You can get the networks there, but you can't get a lot of other information. If you get access to the full data, which we did, which requires a lot of kind of security kind of thing, not security in the classified sense, but just data security, because it contains personal information. A lot of paperwork. Actually, you have to pay for it too, but not a huge amount of money, but you do. But if you do that, you have access to thousands of covariates on these children. So what I'm showing you is one friendship network. So we're used to looking at friendship networks, and the nodes are colored by one particular variable, and you can see that this is not a community type structure, right? This doesn't look like a stochastic block model or anything else. But nonetheless, there is some, it is not completely random, right? There is some clustering, there are some colors that go together. And what this in fact is the age at which the student first tried marijuana. So you can see that it's about half, the light blue ones are never. So that's a censored outcome. And there are other ages, and they kind of tend to go together. So this is where you see cohesion. And if you wanted to either predict what will happen sort of for public health purposes, or you wanted to look at the connection to other covariates that you may know about, you kind of want to take this into account.
Can you say again, please? Never what?
So the first age at which they tried smoking marijuana. This is a question they were asked in the survey.
I see some edges, I think. What are the edges here?
The edges come from the survey. So they were asked to nominate their friends. They were asked a lot of questions. Each student was asked to nominate up to 10 friends, and we ignore direction here. So there is an edge regardless of who nominated whom. And even though they were asked to nominate up to 10 friends, so potentially you could be losing edges, right, because they can't nominate more than 10. But in fact, the average degree of this network is 2.8. So many of them did not take advantage of the whole 10 slots that they were allowed to nominate. So that's what the edges are.
And what do the distances mean?
Well, it's just one of the embeddings where you visualize a network. Right, so there are different algorithms by which you can take an adjacency matrix and try to embed it into D so you can plot it. Typically, it tries to plot it so that things that have a lot of connections are close to each other. So it's sort of one-to-one mapping from the matrix to the plot, but it's just a visualization. So, other questions? Okay. So just to formalize notation a little bit. So we're going to assume we have n data points on which we have an outcome of interest, which we'll call y, and covariates that are going to be used as predictors, x. So that's like a standard prediction problem, but we also have a network that connects the observations. It's not crucial for this that it's symmetric and binary, but for simplicity, we'll just assume that for now. So it's really like multivariate analysis. You have x and y, but instead of thinking they are IID, you now know that your samples are connected by a network. So potentially that is a bad thing, right? Because that means dependency. That means your effective sample size is smaller than you think because your data are dependent. That's potentially a bad thing, but it's also potentially a good thing, because if you believe into this cohesion phenomenon, then it can help you improve prediction, because it actually gives you information. If you know that there's one student who smokes, then it'll help you predict better for their friends. So that's our goal, to develop a strategy that's computationally feasible, first of all, because otherwise there's no point for actual statistics problem, and general, hopefully, general enough to cover different cases of prediction settings where you take advantage of cohesion. But I also don't want to just assume it's there and force it. I want to take advantage of it if it's present. I want to learn if it's there, but I want to be able to tune how much cohesion I'm putting into the problem, because there may not be any, right? Depends on what the response is. Some responses will be much more influenced by social connections than others. So this is going to be something that will be learned from the data. I'm going to start from explaining it in a linear regression setting, just because it's a simple setting that, well, at least the statisticians all know very well. The approach is more general than that, but it's just easier for exposition. So that's what I'm going to start from. So let's say we have a standard linear regression model. Y equals an intercept plus a linear combination of covariates plus error. The one thing here that is not quite standard and that will turn out to be crucial is that there are individual random effects here. This is not a universal intercept. This is an individual intercept that's specific to each node. Turns out that if you don't have that, then cohesion is much more difficult to look for. Everything else is sort of standard. Betas are the fixed effects of the covariates. They're universal, the same for all nodes. X, I'm just not going to worry about large p small n here, because that's not the point of the talk. And we know how to deal with that, right? We can do lasso, we can do whatever. This is not about high dimensional regression at all, so I'm just going to assume that p is less than n and it's a full rank. But it's really not important because we have many tools to deal with them. And the errors, I'm going to, well, this is not even important, so I'm not even worried about it. So in general, you cannot estimate these things, right, in random effects models. If you assume there's a different intercept for every node, you don't have enough data to estimate it. That's why they're called random effects. So what we're going to do to sort of induce cohesion is we're not going to put anything in the model itself. And one reason we're not going to put anything in the model is because it's kind of nice to have this as an interpretable relationship between x and y, because the betas still retain the original meaning if you're just doing linear regression. So what I'm going to do is just add a penalty to, and again, the loss function can be whatever you like, but just for simplicity, let's say it's least squares. So you're just fitting linear regression by least squares, the simplest thing you could possibly be doing, but then you penalize the intercepts to induce cohesion. Why does this induce cohesion? Why is this a cohesion penalty? This is the Laplacian of the network, unnormalized is the diagonal matrix of degrees minus a. Why does this have anything to do with cohesion? Well, if you write it this way, this is just one line of algebra, if you rewrite this penalty in this way, you see that what this is the differences between these individual random effects only for those pairs of nodes that have an edge connecting them. So you're penalizing differences between connecting nodes. And so if you add that, then this will be shrunk, and so they will become more similar. And lambda is just a tuning parameter, which you can choose by cross-validation, and if it doesn't help you in prediction, then cross-validation will tell you that lambda should be small, and the penalty will essentially go away. In this particular case, it's trivial to do this because everything's quadratic. This is quadratic, this is quadratic, so you just solve it, closed form. There is an inverse you have to compute, so you have to ask yourself, when does it exist? It exists almost always. There's if you can write down exactly the condition for it to exist, which is sort of saying that none of the column space vectors of X are in the null space of L. That's not going to happen really, right? But if you're worried about this, you can always just add a small constant to the diagonal, then it will always exist. And in fact, you might want to do this anyway, because this will give you the regularized Laplacian, and people who have studied concentration properties of the Laplacian on networks actually know that that's a good thing to do. It concentrates better, it generally behaves better, so you might want to do this anyway. So existence is really not an issue. But if you want to think about it statistically, you can also interpret this as adding a ridge penalty on the alphas themselves, which is also a reasonable thing to do. The computational cost of this, well, it's closed form, but you do have to invert a fairly big matrix, n plus p by n plus p. Of course, depends on how big your data is. If the Laplacian, or if the network is sparse, and therefore the Laplacian is sparse, this can be inverted pretty efficiently, because there is this standard strategy called block elimination, by which you can first invert the sparse matrix, which you can do relatively cheaply because it's sparse, and then you do this block elimination thing that reduces the cost to just inverting the second matrix, and that's p by p. So that's what you would have to do if you were just doing regression without adding any Laplacian. So that's just the standard OLS cost. And this is n plus the number of edges. So that helps if it's sparse. If it's dense, so if the number of edges is in the order of n squared and n is large, that this could become costly. You could do something else. You can first sparsify the Laplacian. There's a whole literature on sparsification, which is mainly, I guess, done in computer science. Sparsification just simply asks the question, given this Laplacian of this network, how can I construct a sparse Laplacian that is as similar to it as possible? What's the good efficient algorithm, accurate algorithm? And people have come up with a whole number of different algorithms. But what this means is that for a specified accuracy, epsilon, so here's the epsilon. So you want to construct a sparsified version, L star, from the dense version L, which is a good approximation. And then there is an algorithm that can give you a sparsified version with that many edges. So it's on the order of n log n, but it depends on how accurate you want it to be. So if you want a really small epsilon, then you're going to pay the price for that. But the cost of constructing this thing itself is n squared. Just doing it, just computing the sparsified version. So if you're only going to solve the system once, there's no point doing this because you're already paying the price of n squared and you're losing accuracy. But if you're going to do an iterative algorithm, say if you're not doing linear regression, if you're doing generalized linear models, so you have to do this inversion in every iteration of something that you're fitting, or you're computing a solution path for all the different lambdas, then it's worthwhile because you can pre-compute it once. You just do it one time and then use the sparsified version. You may never need to worry about this unless your n is really large or you are in a lot of hurry. But if that becomes an issue, there's in principle something that you can do. Questions?
I really like the penalty term there. I think there's another way to look at the penalty. So the Laplacian matrix can be also written as the B transpose B, and B is the edge incidence matrix.
Say that again. Laplacian can be written as what?
B multiplied by B transpose, and B is the edge incidence matrix. Then your penalty here, this alpha transpose L alpha, can be written as the L2 norm of B multiplied by alpha. And here you're using a rich penalty-like thing, but you can also think this, well, I just put L1 penalty there. It's the L1 norm of B multiplied by alpha. I guess in that case, then the objective function you are written there can be solved by generalized lasso without taking the inverse of Laplacian.
Well, yeah, it's not necessarily going to be faster to do lasso. It may be. I guess it just depends on whether you want to force some of them to be zero or not, right?
Yeah.
So if you switch to the L1 penalty, you will have an additional feature that you will be just making some of them the same. But yeah, you could do that.
Yeah.
You could. There are different. You could take a different representation of the Laplacian, right? You could normalize it. You could. There are different kinds of things you could do. That's just the kind of the spirit, the main point. But I'm sure there are different ways of doing it as well. Other questions? Okay, so this has a Bayesian interpretation. Those of you who know me will immediately realize I didn't come up with this, but my student did. He's better versed in this than me. So it turns out you can in fact write it as a fully Bayesian model. You can put a prior on alpha and on beta, and you assume the usual kind of normal model on y with alpha plus x beta. If you put a non-informative prior on beta, so Jeffrey's prior, and then you put some prior on alpha that has cohesion in it, and in fact if you want to match it directly, then this turns out to match exactly the estimator. So it's a Gaussian Markov random field prior, right? So somehow you think there is underlying space in which these points live, and there is a distance, and if you put exactly this thing as the covariance matrix for the Gaussian MRF prior, and this in the Bayesian literature this is called improper intrinsic GMRF prior, then you get exactly this model, and this becomes the map estimator for this Bayesian model. So if you're so inclined, you can look at it this way and do the whole thing in the Bayesian, in the full Bayesian framework. Another thing you have to worry about a little bit is if you're going to do predictions, you better have an algorithm for out of sample points, right? So new points come in, new students join the network, and you fit the model on some part of the network. Of course, you have your X and your beta, but what are you going to do with alpha, right? Alpha, individual random effects that you need new ones for new people, so you have to compute them somehow. So what we do here is, given that we already have on the first part of the network N1 nodes, we have alpha hat 1, we already fitted the random effects, and we have beta. We construct the Laplacian for the new big network, put them all together, and then basically make them as cohesive as possible with the fitted random effect. So minimize this penalty term, which is just a little formula. It's all quadratic, so you just solve this. And then you predict y by plugging in these new estimated individual random effects plus the fixed effects. You always have to do something like that when you have individual random effects. So that's not really a complication of our model. That's a complication of having individual random effects.
In that case, don't you have the problem that you might get your Laplacian changes when you add new nodes to the network?
Well, so this is the Laplacian of the whole combined network. So this is this is the old one, and this is the whole.
Well, that's what I wondered. So the L11, is that the old one? Because the degrees will change if you add new nodes to the network. So your D11 is maybe not the same as the.
No, sorry. Okay. No, this is just the combined Laplacian. Okay, you're actually right. It's not necessarily the same. It's just I'm just writing it partitioned because of this.
Right.
Yeah, it may have new edges. So yeah, just take the big Laplacian of the new network. Okay, so when we actually first did this, I spent weeks, if not months, thinking somebody must have done this because this is just too obvious. But we never quite found this exact thing. But there are, of course, connections to other things that people have done. So let me point some of them out. The repeated measurements model, a very old classical statistical model where people have groups, and within each group you have repeated measurements, is sort of a special case. You can think of a group as a clique within a graph. So everybody in the group is connected. Everybody has the same value, the same random effect. And then between groups there are no connections. So it's a more specialized structure, but it is related. If you just think of mixed effects models, we are using the mixed effects model as our basic unit in regression. At least mixed effects just means you have a random effect and a fixed effect, and we have a random effect, which is just the intercept in our case, and a fixed effect. But mixed effects models in the usual classical statistical setting do not have any cohesion feature. Any dependence between units is not allowed, more generally. They have to be IAD, so it doesn't really do this either. Probably the closest connection is to what people do in spatial statistics, where instead of an adjacency matrix, you have a matrix of spatial distances. And you assume some kind of smoothness in space. So you typically think, say if you're doing temperature prediction, if you're doing climate modeling, you think your temperature in one location is going to be fairly similar to the temperature in the adjacent locations. And there are all sorts of spatial models that do this. Say, conditional autoregressive model is one of the commonly used spatial models. That's quite analogous to ours if you convert spatial proximity into kind of a network adjacency matrix. But typically the full spatial models are much more expensive to fit. You usually have to do MCMC. And of course they also assume a spatial distance. There's really some meaningful distance in space that they rely on, which we don't have here and we don't need it. So there is a connection, but it's not that direct. And if anybody thinks of other things that look connected, please let me know. I'll add them here. Just very briefly, some theoretical properties. This is not the kind of theory that most people here do. This is not the kind of theory I myself have been doing for a long time. This is very It's just regular regression theories, easy stuff to compute. But it's instructive to look at just to understand some trade-offs. So these are not very interesting bounds, but you can compute bounds on the mean squared error for alpha, for beta, and also on the prediction error. You will recognize some things like this, right? This just comes from linear regression. There are other things that sit here, various eigenvalues of various matrices. The one thing that you see everywhere in all of these is this term. This has a name. This is called cohesion gradient. Cohesion gradient. I have the next slide on it, but. So this being small is good, right? This will give you smaller bounds. In fact, if it's 0, then you could also show it's unbiased for beta. And this name we didn't come up with. This is what the physicists call this quantity. It's the derivative of this penalty. It's the Laplacian times alpha. And its meaning in physics, in fact, it's used to talk about heat diffusion. Its meaning is measuring the difference between a node and the average of its neighbors. And so that makes sense, right? If this is small, if the neighbors are similar to the node, then we have a lot of cohesion, and the method will take advantage of that, and it will do it. And in fact, if we're willing to assume that this was small in a certain sense, right, this is not divided by anything, so this is the right scaling, then we can get a consistent estimator of beta hat for a suitably chosen tuning parameter. Yeah.
Lisa, this gets back to a point you made earlier, which is if there's different versions of the Laplacian. I guess the way I think about the normalized Laplacian would be sort of sum of squared distance between the alphas that is normalized by the degree of the vertices in question. Do you know, does the cohesion gradient also have an interpretation there, or in the sort of diffusion theory stuff, is it typically the unnorma? I mean, I'm just sort of wondering, like, can you shove in sort of any Laplacian? I mean, the scalings will change, of course, the normalization will change, but is there ever a reason from the sort of physics perspective, the heat diffusion perspective, that you'd ever shove in a different Laplacian here? I was just thinking about
No, that's a very good question. I honestly don't know enough about the physics interpretation to know what the meaning would be. I think this naturally arises out of some equations that they write, but it could also be that the other one also has an interpretation. From the statistical point of view, yes, you can, right? Yeah. You can shove in a different Laplacian, or in fact some other representation of how you want these things to be. Yeah. But I mean, this one I think is quite natural because it is just pairwise differences, right? So it doesn't
there's no additional normalization.
There's no additional normalization, but you could believe that you want this to be weighted by degrees, right? Yeah. Or some product of degrees, or your favorite function of degrees, right? So yeah, you could.
Yes. So in this case, the gradient here is just the sum of the differences. So that means that it's really not the difference between node and neighborhood average, but that multiplied by the degree. So exactly. As you say, if you want to normalize by the degree, you will get the difference and the neighborhood, which maybe is reasonable. But I'm not sure also, each edge has 2 endpoints, so I don't know really which combination of the weights one should use here. There are certainly several possibilities.
Yeah, exactly.
Yeah, I think that's kind of the difficulty, because the degrees go with nodes, and this thing goes with an edge, right? And so then you have to.
Yeah. But I mean, I bet you could. I mean, it might be possible to get variants of theorem too that just have different scalings for the, for the operator, or for the norm.
Yeah, because there's nothing. There's nothing in the calculation that stops you from just having another term. And
Cool.
So this is, you just get if you take the norm squared, you just get alpha L squared essentially. So really it's just
it's just really it's really the same. It's where did I write this? Yeah, I mean this is equivalent, right? One goes to 0, the other one goes to 0. It's just because this has a name in physics and they used it, I wrote it this way, but yeah. Okay, so
Maybe just following up on this, you just call alpha always a random effect, but right now you're just estimating it as a fixed effect, aren't you?
no.
Because you also talk about the mean squared error of alpha.
So, well, yeah. So, right. So this is the difference between being fully Bayesian about it or not. So when I'm calling it a random effect just because I'm saying there's a different one for every node.
Okay. Effectively, it's the Bayesian interpretation of your.
So yeah. But I mean, this is always a difficulty when you're going to, if you're doing random effects, if you're doing mixed effects models, you have this thing that is random, right? So you can't really estimate it. But then you actually always have to estimate it if you're going to make any predictions. So people compute the, the best predictor for alpha and plug it in. And for the philosophically, it's dodgy, but that's kind of what you do. With this. I learned a lot about mixed effects models that I never knew before. It's not something, it's more of a biased thing, but there's a decades and decades worth of methods for that. More questions? Stop. Okay. Another thing you can do, maybe somewhat instructively, is once you have this bounds, just compare the error to what you would do if you just fit this model by least squares. Your intuition about penalties, because we're all used to thinking about the lasso, right? You think, what does the lasso do? It introduces bias, right, and introduces variance. This thing actually does the opposite. Because it's nothing to do with the penalty on betas. The bias here comes from the dependence in the observations, and it actually reduces the bias, but it increases variance. And if you're just in the simple regression context, if you're comparing it to what would happen if you didn't have this penalty, just to fitting by least squares, you could actually calculate these things. And your increase in variance has this form, and the network is here. It's just hidden in this eigenvalue, this new. You go back to it, or is it? It's something that involves the whole thing. And the decrease in bias, in squared bias, is also here. So, and again, this quantity appears. So, intuitively, again, the smaller this is, the more decrease in bias you will have, the better your method will work. But there is some baseline below which you won't beat least squares. So it's not always better, but I should look at it. And you can also compute this separately for alpha and for beta. They're slightly different equations, but they're sort of the same spirit in comparison. And we also proved this guarantee for specification. This is just to be complete, just saying that we were basically using the results that people have gotten in the specification literature. If you compute the estimator with the sparsified version, we can guarantee that it'll be close enough to the full estimator with something that again depends on this cohesion and depends on how accurate the approximation was in the first place. And in fact, these results, this was all written down for least squares because it looks nice and you can make comparisons to OLS, but you can actually do the same calculation more generally under convex general loss functions. So say if you wanted to do it for GLMs, you could get similar types of bounds. So, okay, what can you do beyond linear regression? And of course, you can put whatever you want into X. So I'm not saying you have to fit a linear model. You can put in nonlinear terms and interactions and whatever you want. That's obvious. If you have a lot of predictors, you can add your favorite penalties and beta, because that's completely separate. So you could do lasso. You can replace least squares by a general loss function by M estimation. You can do logistic regression by doing generalized linear models. We've actually done it for the package we have, which is on my students' website, does both linear models and logistic regression, and also Cox proportional hazard model. In GLM, it's particularly clear how you do this because GLM runs on a least squares algorithm. Right? The way you actually fit a generalized linear model is by iteratively doing least squares. You just replace least squares with this regression with network cohesion, and then you're done. So you can use this idea more generally. Because I want to go back to the picture that I showed you with marijuana use, I want to say a couple of words about how you extend it to the proportional hazards model. It requires like one tiny little bit more thinking. So Cox's classical proportional hazards model relates survival time, so time until an event, which may be censored, like in that application. Some students at the time you interview them have not tried marijuana, maybe they never will, so you just don't see that time. And you model the hazard function, just the hazard that the event will occur at time t, as some baseline, that's why it's called proportional hazards model, times this function, which includes the covariates, and also for us here, the individual effect. The baseline cannot be estimated, so you only look at the ratios. And the standard way of fitting this model is through something called partial likelihood. You can write it down. The log partial likelihood looks like this. And so it's a loss function, and you can stick it into that framework and maximize it. The only thing you have to add as an extra little bit is, because it's all proportional, it's invariant under a shift in alpha. If you do a shift in alpha, it'll just get absorbed into the baseline, and you won't be able to estimate it. So you basically have to assume that alphas are mean zero, because otherwise you can't estimate the shift. And conveniently, you can just enforce that here by the ridge, from the ridge penalty. And then you interpret the alphas as the deviation from the baseline, so higher or lower than the average population. Now that's really all. So let me show you a few numerical results. First, just very quickly, a simulation, just to kind of check that it does what we expect it to do, and it's not insane. So here we generate a network from the stochastic block model. So it's really like a group effect. 300 nodes, 3 equal blocks. Between block probability of connection is 0.1, within probability is 0.5, so fairly dense network. And then these individual intercepts we generate from the normal distribution, which has a different mean for every block, right? So there's cohesion within blocks. And the variance controls how cohesive it is, right? Because if it's a large variance, they actually will be quite different, and there's not much cohesion. If you make this S small, then there's a lot of cohesion. So that's the parameter that controls how much of it is going on. And then just betas and x's are just generated from normal. And we do this for both linear and logistic regression. So what do we compare it to? The baseline is just least squares by itself, or logistic regression by itself. It makes sense to compare it to an empty network. What if you didn't have any information, right? Then it just becomes ridge regression, and you just have a ridge penalty on alpha. And it will actually always give you the same estimate of beta, or almost the same. And we also compare to sort of the best we could do here to the Oracle model, which of course in reality you don't have, is you fit a fixed group effect for each block. So you know the blocks, and you know they have the same mean, and so you fit a group effect. So for linear regression you get, so what's plotted here is a relative improvement over OLS. So if it's the same as OLS, you see 0. So the null model, which just adds the ridge penalty, is essentially the same. Some of these points are actually slightly and it's not numerically exactly 0. Some of them are slightly higher, but it's very, very tiny. You don't see it. And this purple curve is the cohesion penalty. The red curve is the oracle. So you can see that at times they actually cross. But essentially, you see what you expect is that if there is cohesion, if S is small, so the blocks really do behave similarly, you gain a fair amount, and then as cohesion dissolves, it just becomes like least squares, which is what we wanted to do. We don't want to impose something that's not there. So then the effect disappears.
What did you assume known when you ran your method?
Known what?
You need the graph structure for your method, right?
Well, so the graph is the block model, right?
So you assumed you know as much as the oracle?
No. I just take the graph generated from the block model. So I just take whatever comes out of the block model for my method. The oracle knows what the blocks are. I don't know what the blocks are, and I don't fit the blocks in any way, because I'm not fitting a group effect. I'm just doing cohesion overall. So I don't know anything about the blocks, and in fact, it doesn't matter to me that this came from a stochastic block model. It could have come from anywhere. Logistic regression, basically you have a similar phenomenon, except the oracle does better, but you still improve over the null model. Actually, the null model itself improves a bit more. You can see that quite different things for alpha and for beta, and also for estimating the probability. There are some, I don't honestly know why this happens, and my student has some very elaborate explanation, which I don't believe, but there's qualitatively, we still see that you gain when there's cohesion, and then the effect goes away. And also there are quite different things for alpha and beta, and you would expect this, right? You put a rigid penalty on alpha, it doesn't really do anything to beta, but it improves the estimation of alpha more here. And it actually also happens in linear regression, you just can't see it on that scale, because scale is different. All right, so let me show you a couple of data examples. This one we just picked because there was a fairly influential paper in the econometrics literature which proposed their own model for this, and I'll tell you what their model was, and analyzed this exact data set, so we wanted to compare it to their results. And the data here is one of those schools from the EdHealth study. It's actually the largest school, if you take from the survey, which has nearly 2,000 students. The friendship network I've explained already. The covariates, there are many more covariates, but the covariates they have used in their model, which we will also restrict ourselves to, are mostly categorical things like age, not categorical, and grade, sex, race, whether the student was born in the US, living with mother, father, etc. Because we want to see kind of what happens as we make the model richer, we just also do adding one variable at a time in the usual forward selection sort of way, but we want to learn that separately. So what we did is we took the largest connected component of that network. The largest connected component is 871 samples, and used that as the network, and we used the remaining variables without any network information to just determine the order of the variable for forward selection, to add them to the model one by one. And what they're trying to predict here is recreational activity, which they measure by the number of extracurricular clubs or organizations the student belongs to. So it's an ordinal variable, but it has a number of levels. So before I show you the result, let me just mention quickly the model that has been, or different variations of this model have been popular in the econometrics literature, where people actually spend a lot of time looking at things like that. So this is the model they have used. What this basically says is so you have your covariates for that node, also average the covariates of the neighbors and average the response of the neighbors and stick that into the model just as extra predictors. So empirically that makes a lot of sense. it does become an autoregressive model, so if you wanted to properly fit it, you have to do something more complicated. They just do regression once they add them as predictors. But if you think about the form of cohesion it assumes, it's a very particular form of cohesion. It's actually quite a rigid structure. It's a linear combination. It's the average of the neighbors, and it gets added with a certain coefficient, which is the same for all of them, and for the x and for the y. So it's a much more structured model than what we are doing. And that they call that the social interaction model. So here are prediction errors. I'm not showing, well, I can't here obviously show parameter errors because I don't know what they are. It's real data, so I'm just showing prediction errors. The null model with no network information and OLS, they're not exactly the same, but they're the same to this precision, so they're just shown here together. This is the social interaction model, this is our method. And this is in order. So first you start with the intercept only, then you add what turns out to be the most predictive variable according to forward selection on a separate validation data, mother's education, then born in the US, etc. So these are getting added to the model, so the model is getting bigger at every step. One thing to note is that the very first number here, the regression with network cohesion with no predictors in the model at all, this number is smaller than any numbers in these two columns. So immediately, as soon as you force cohesion, even without worrying about covariates, you do better than what you can predict from covariates. They all follow the typical regression thing that you would expect to see as you're adding important variables to the model. The error goes down, then it stops going down. You just nothing else is really happening. Of course, this doesn't mean that these are the true variables, right? Remember that association is not causation. We just pick them by forward selection. Some other order may have given you the same errors. But it looks like you've explained what you could explain with covariates by about here, 3 variables. And that is fairly consistent for all of them. So they all have their smallest error at this point, and then you just become adding nulls. But for every single row, if you look row-wise, it is always better to take cohesion into account. It is doing the social interaction model also helps. Doing it in that particular way is better than doing OLS, but not as good as and to go back to the marijuana use example, just a little bit more information on this. There are all these complications about at-health data. There's in-school interview and at-home interview. The at-home interview or in-home interview. In-home interview was only done for a fairly small subset of all the students who did the in-school interview. The in-home interview is much more detailed, and this kind of marijuana questions they only ask in the in-home interview. They don't ask that in school because I think they don't think the students won't answer. And they ask them twice to nominate friends in school and in home, and of course they're different, right? So just that reminds you the whole accuracy of this whole process is a little bit questionable. But so we just use the in-home interview for this, again for the largest school, different number of nodes because different response rate. But for the full, so here you can see how many covariates you really truly have for this data set. If you use the full long form, that's a lot. So we again split it and used roughly 2/3 of the data for forward variable selection just to organize this table, and the rest for evaluation. So the part we used for evaluation is a connected network of roughly 600 nodes. Still very sparse, average degree is 2.8. And we fit Cox's model. Again, Cox's model, everything is a little bit weird. How do you evaluate prediction, right? So you're predicting survival time, and some of it is censored. So there's a standard tool for that in the literature. It's called predictive partial log likelihood, PPL. used for evaluation of Cox's model, and it's sort of this difference between the likelihood of the full data and the likelihood of the training data. This is standard, just that's what the measure is. So again, if you look at this, here we can't fit the social interaction model at all because that's just linear regression model. There's no analog, which is another advantage of doing it this way with a penalty, because you can really put it together with any model you like. So we just have the standard model without cohesion. Again, it's the same as the one with a ridge penalty, a small ridge penalty. And again, this number here, the first number with no covariates, is better than the best you can get with any number of covariates. The covariates don't help immensely here anyway, but they help a little bit. When you add the first one, which is have you received school suspension, which kind of makes sense, you do a little bit better. I don't know why driving a car is that important, but that's just what came out. You can also look at the coefficients. This gives you the more detailed version of the questions from the survey. And you see the coefficients, they're not the same, of course, but they kind of go in the same direction and they're comparable. So if you're doing interpretation of the betas, which is really something separate that I haven't focused on, the interpretation is not that affected by cohesion. Well, the sign only flips here, but this is very small, so this is basically insignificant. But you're doing better prediction on what you actually take out of your model. And you can get extra information out of it other than just the betas, because you get these individual effects, which here are plotted using the color to indicate whether it's positive or negative, and the size to indicate the magnitude of the individual effect. And remember, in this hazard model, it's relative to the population baseline, so it's higher than average or lower than average. And you can see that in the estimated effects, there is clearly cohesion as well, as there was in the data. Almost done here, so let me just briefly summarize. The good things about this is that the strategy is universal. It's not part of the model, it's just a penalty, so you can apply it to many existing models. We retain the original interpretation of covariates, which is something that I really wanted to do, because if you start putting other regressors in, the interpretation of the coefficients changes and becomes less clear. We have a reasonably efficient computation strategy. Computation is not that big a deal here anyway, because most of the time it's quadratic loss functions, but you can make sure it's reasonably fast. And empirically, we find in applications that you get significant improvement on using covariates alone as soon as you put in cohesion. Many other questions you can ask. One thing you can ask is what types of network structures make this effect more important or less important, right? Cliques, clustering coefficients. We didn't look at that at all. We treat the network as fixed. It's conceivable that on some types of networks, the cohesion effect will be much more prominent than on others, or it will spread faster and things like that. That's really a different question, but it's an interesting question. One can look explicitly at network or data models that have cohesion in it in a general way. You could look at other estimation problems other than prediction, and look at whether cohesion can help you there. And many other things that you can do with this. I'll stop here.
I have a question. So you mentioned you are using cross-validation to choose lambda, right? How do you do cross-validation on this network?
So we just do it in the standard regression way, split the observations. We have a way of predicting, right, the random effects.
So you are not
They're
trying to
missing.
maintain the network.
We're not trying to cross-validate on the network. We just cross-validate on X and Y in the usual way. It's a good question. And there are different ways on how to cross-validate on the network. By removing edges, removing nodes, you can try doing these things. We actually did compare a little bit on different ways of doing it. It doesn't seem to matter here, maybe because this is fundamentally a regression problem, right? We're trying to cross-validate for predicting Y from X. And so just splitting it naively was fine.
But the penalty terms may matter a bit, right? Because
Yeah, but so we tried to do it in a kind of smart network-aware way, and we did it in a naive way, and they choose pretty much the same tuning parameters. In this context, I'm not saying that that's universal, but in this context, because I think we're not tuning for any network model fitting, right? We're not really. If you were tuning it for like block model fitting or community detection or link prediction, it would matter more. We're tuning it just for prediction error, for regression, and so empirically, I don't have any theoretical justification of this, but empirically we didn't find a difference.
Yeah, I mean, this might be getting at a question I was about to ask, but I was struck by the nice framework or formalism of being able to go from the observed network structure to sort of known network structure. I wonder if there's something in between, a little bit akin to link prediction or the fitting of a network model, where you'd almost replace the observed adjacency structure with the mean fit under a model or with an EM algorithm or something like this.
Yeah.
But maybe, like you're saying, I mean, you said in cross-validation it didn't seem to make a lot of difference, but I wondered if
Well, yeah, so this is kind of the second bullet point there, right? Potentially, right? So instead of saying, so I think it's going to depend a lot on what exact model you're going to assume, and you're going to have a trade-off, right? Because once you assume a model, you will probably do better if your model is correct, and probably not otherwise, right? So, but that's not to say we should never fit models, right? But so this is just something we haven't done, but that's very much a good direction because you're right? We just take the network as fixed and don't think about it at all, or else we don't have it, but you could do something in between.
Yeah, I guess you are technically, if you want to think of it that way, you're just conditioning on it right now. So
Yeah, we're conditioning on it, exactly. But you could just, take it one level up and,
cool, thanks.
Okay. So I have actually two questions, but let's start with one. So your alpha is actually, you can interpret it as a latent variable.
Sure.
And so you would have a univariate latent variable that lives on your network.
Mm-hmm.
And basically distances on your network then are calculated on this latent variable that that only comes into action when you are actually close to each other, or if you're connected by an edge. I was wondering if you could extend this to maybe a two-dimensional latent space somewhere that is embedded on the network. In fact, would that help? Now it imposes a certain distance, like if there's a triangle, in your network. Your alpha of the one will impose a certain structure between those three nodes, basically, that are there, which you could enrich by making alpha two-dimensional or three-dimensional.
So, it's conditional on the network, right? So I don't know.
No,
Right.
it is conditional. I'm not saying that we're not conditioning on the network, but basically alpha is a univariate, and you could actually generalize this to multivariate.
Well, so I think if you took it all the way to the latent variable representation, you could, nothing's stopping you from doing a latent variable representation of the Laplacian, right? You could take your k eigenvectors and use those coordinates and put them in as predictors, right?
Laplacian is given, but it's the alpha. The alpha that is basically your latent variable. So that's what I'm kind of. But you now take it univariate. You could just.
Yeah, you could. You could. You would just. I don't know how. Whether that model would be even fully determined, right? It's already.
Oh, you need to.
You'll need some identifiability thing, rotation thing. Well, yeah, you could in principle. I would worry a little bit about like.
Yeah, whether it's useful, I don't know.
Right. You'll need to regularize somehow, right? Because otherwise, you can just add many alphas and fit it perfectly, right?
Yeah.
So, but yeah, you could.
Have you thought at all about a situation where instead of having essentially a response for each point, you have a single response to the network, but you have a whole series of networks, with the networks being, okay, so now you have to make some model assumption that the sense that the networks are generated similarly, right? I mean, you have independent copies of the networks. And that,
I actually thought a fair amount about it. That's a different talk. But but this comes up in brain kinectomics, which is maybe why you're thinking about this as well.
I think about it in another.
Oh, you're thinking maybe it in a genomics context, but yeah. So I have done some work on brain data where you exactly have this situation. You have multiple patients. Each patient has their own network, and then you have some sort of response, like their disease status or whatever, and you have covariates, which are patient, et cetera. I don't know if there is a direct connection between this setting and the other one. You can, of course, induce cohesion there as well within that network, but how you sort of do it across networks, right? Do you assume that it's the same for all of them? I haven't tried to apply this in that setting. I'm aware of the setting and it's different, but yeah, potentially this could do something there.
Actually, what made me think of it was more, at least I've been told, and have some sense that this is this kind of framework in which deep learning particularly succeeds, right? You have not networks, but you have, they take advantage in some way of the dependence between the covariates.
Yeah, maybe I don't know,
Anyway.
but yeah.
Be a good point to
All right.
start our coffee break and continue discussion. And thanks again to Lisa.